So next we have Andres Castillo from Stanford University, whose field is multidisciplinary computational sciences. He's an LRGF fellow and is doing a residency at Sandia National Laboratory in New Mexico.
Awesome. Thank you guys very much for coming. I'll be talking about plasma kinetic modeling and theory of shear flow instabilities related to cross-field diodes. So I'll do the acknowledgments first. First, thank you all very much to my mentors, my advisors, people I've worked with throughout to do this work. My advisor, Dr. Hara, my mentors at Sandia, Matthew Hopkins and Nikki Bennett, and also Anubhav Dwivedi. And yes, thank you very much to Sandia, to the Krell Institute that made this work possible. So basically the work is motivated by magnetically insulated transmission lines. They are an important component of pulse power systems. For example, at Sandia there is the Z machine. It's essentially kind of the last component here in the central part before it reaches the load where you're trying to deliver this high power pulse to a central load. So this is essentially kind of a cross-sectional view of what a magnetically insulated transmission line looks like, or MIDL. In this work, we're going to take an even more simplified look of what a MIDL is and think of it as a cross-field diode by looking at just a part of its cross-section here. This is essentially what a cross-field diode is, where you have anode-cathode gap in vacuum, and you have an electric field established by anode potential, and then you have a magnetic field that's perpendicular to that. And so then when you have electrons that come out of the cathode here, they have what's called drift due to the perpendicular E and B fields here that flow across. And essentially you have the passage of current that's going through the electrodes to deliver to the load, and the flow of the electrons contribute to that. So the, I guess, motivation here of the study is a problem that can occur in MIDLs, where essentially we're focusing on the area here where in the ideal operation you have just an electron layer that's flowing, but you can also have a contaminant plasma layer that forms, particularly hydrogen plasma. And essentially this can kick off what's called mainly a Kelvin-Helmholtz type of instability, but it's a shear flow instability. And once you have the shear flow instability, that can enhance or allow for the expansion of this plasma across this gap. And essentially when you have the plasma expanding from the cathode to the anode, that's current that's being taken away from what's supposed to go towards the load. So this is an issue called current loss, or also called parasitic current. And so that's kind of what we want to study, these shear flow instabilities and their relevance towards MIDLs. So this is in two parts. First, I'll talk about the theory, where the main thing that we're going to do is we're going to propose a different way of solving for the growth rates of this instability. And in doing that, we'll learn a little bit more about what this shear flow is like in cross-field diodes. And then we'll go to the second part. We'll do some plasma simulations called particle and cell simulations. And then we'll use the theory to make comparisons with the growth rates we see in the simulation. So with the theory, we'll start with this simple view of a planar cross-field diode. We start with an equilibrium state where you assume you have some electron density profile. And in this analysis, it'll be with electrons only. And in the future, we'll want to add the contaminant plasma layer. But we start with just the electrons. You have some profile that's in the x direction. We assume that the velocity of the electrons are that drift velocity, the shear drift velocity called E cross B drift, which, as you see, is a function of the electric field and the magnetic field. And then the electric field, through Gauss's law, is essentially just the integral of the electron density, and that's how you get the distribution of the electric field. An important assumption that's often made in cross-field diode work is that you assume that you're in what's called a space-charge limited regime, which is that enough electrons have been kind of pumped out of here that it's reduced the local electric field to essentially to be zero at the cathode surface. And so that's the boundary condition that's imposed here. And through this relationship, we get this connection that becomes important that I'll discuss later. But essentially, the gradient of the velocity in this section is essentially equal to a ratio of plasma frequency to gyro frequency, where the plasma frequency is a characteristic frequency that's dependent on the electron density. And so we have this equilibrium state. Essentially, we do a perturbation of the system to then see what would be the growth rates for the instability. So we then have perturbed quantities for the density, the velocities in the x and y direction, and the electric field in the x and y direction. where it has a wave number in the y direction. And so with these perturbed quantities, we have 5 quantities that are unknown, so we need 5 equations to solve this system. So here are the linearized system equations that we use to solve it. We have the continuity, the momentum equations, Faraday's law and Gauss's law. Here we've assumed electrostatic assumptions, so we assume that there is no induced magnetic field, or the induced magnetic field is very weak, so it's not considered. But we also did this analysis in the electromagnetic system. It would just become, we just have an extra unknown, an extra equation, and it makes it a larger system, but it's the same process. But here I'll talk about the electrostatic one. And so with these 5 equations, with these 5 unknowns, we can then combine them to solve for this system. And essentially, first we do this in normalized variables. The main ones I want to highlight is that when I'm talking about frequencies, I'm really normalizing them by the gyro frequency, so the frequency of the gyration of the electrons due to the magnetic field. And I'm also going to be talking about this parameter Q, which is just the ratio of the plasma frequency squared to the gyro frequency squared. But you can think of it as just a normalized electron density, and that's what Q essentially means. We also use this value here, phi, which essentially just represents the perturbed electric field in the y direction. And essentially with those 5 unknowns, with those 5 equations, we can then combine them and we solve for this complete eigenvalue equation, where phi is the eigenvector and omega is the eigenvalues, where the imaginary part of omega will be the growth rate of the instability. And so one thing that I wanted to know about this eigenvalue equation is you'll see there are some expressions in the denominators which are expressions of omega, of our eigenvalue, which have important physical significance. First, there is this S, which essentially is just the Doppler shifted frequency. And essentially when this is 0, this is called a synchronous resonance. And then when we have Doppler shifted frequency reduced by 1, which is normalized by gyro frequency. This is essentially just a gyro resonance. When the Doppler shifted frequency is equal to the frequency of gyration, that's a gyro resonance. And then the last one, which isn't discussed as much, but I'll talk a little bit about today, is that when you have your Doppler shifted frequency equal to a gyro frequency that's reduced by plasma frequency. So this is what we're calling a modified gyro resonance, and I'll talk about this in a little bit. And so this equation 1, this is what we need to solve to get our growth rates. And essentially what we're showing here in the work today is that showing a different way to solve this equation that has some advantages. So the way that it's normally been solved in the past in the literature is that essentially for a given input profile, for a given equilibrium state of electron density and velocity, you choose a wave number that you're trying to solve for. You're solving the eigenvalues and eigenvectors for the equation. So essentially you start with having boundary conditions, which is that phi is 0 at both ends, at the cathode and at the anode. Essentially what you do is something called the shooting method, which is where you guess a solution, you guess a value for omega. And then with that omega, you then solve the equation from the cathode side, knowing that phi is 0, and you solve it down over to the anode side, and you see if it met the boundary condition or not. And if it meets the boundary condition, that means that was the correct eigenvalue. And if not, then you have to iterate and you do a different guess, where in this case we do a Newton solver to converge towards a solution. But so in this method, essentially you have to have an initial guess. You kind of have to know, have some idea where to start, and it's an iterative process. And also there could be more than one solution, so sometimes you have to do this process multiple times with different initial guesses to get all your solutions. And so what we wanted to do here instead is transform the equation we had in the previous slide such that it's in a polynomial eigenvalue problem form. So essentially, this is kind of a generalized way of looking at the equation in the previous slide, where essentially you have these coefficient expressions of omega, these 3 terms. And essentially, you kind of just pull the eigenvector phi out of that, so that now it just becomes a single operator that works on phi, where A is all these coefficient expressions and these first and second derivative operators. And essentially, when you discretize it, this capital A becomes the coefficient matrices of a polynomial eigenvalue problem. And so you can take it a step further, and I won't go too much in the details, but you can further manipulate this polynomial eigenvalue problem, and there's many ways to do it. And this is just one way to do it, where you can now make this much larger matrix equation. But now you can put it in what's a generalized eigenvalue problem, which we can see here, which is another way to solve for these eigenvalues. And so basically we just did a comparison between the three methods. We have the shooting method, which is what's usually used, the polynomial eigenvalue method, and then the generalized eigenvalue method. And so here what we're doing is a comparison of these three. So first we need the input conditions, which are shown here in red. Here is an example of what an electron density profile could look like in a crossfield diode. This shape is based from this equation, which was based from fitting onto plasma simulations results. So essentially from the kinetic simulations, the electron density profile tends to have this type of shape. And so we use this type of shape profile as our input. Okay, and essentially with that, we can then solve equation 1 through those three methods. And we can see here with the blue circles from the shooting method, we get these two results. And with the polynomial and the generalized eigenvalue method, we also get these two, but we also get this additional branch of solutions. And essentially by studying this with different input profiles and for different wave numbers, we're able to confirm that these solutions that the shooting method and these other two were able to obtain are connected to shear flow instability. We're able to confirm that this method is able to get that, but it has the advantage of not needing an initial guess and not needing to run multiple times. But what we saw is that the shooting method was not able to grab this branch, and so we wanted to kind of understand where that was coming from. And so to get better insight, what we did is we, on top of these solutions that we got, we plotted on top those resonant frequencies that I discussed before. The synchronous resonance, the gyresonance, and the modified gyresonance. And essentially what you can see is that this branch of solutions is exactly connected to this modified gyresonance, whereas now you can see that whenever Q, that ratio of plasma frequency to gyre frequency is larger than 1, that means that your modified gyresonance has an imaginary component, and that's where this branch comes from. Essentially that means this is an area, this is connected to the part of the profile where Q is larger than 1. And when it's doesn't have a magic component, it's connected when Q is less than 1. And so we want to get, okay, physically what does that mean? We see that where that comes from the math, but what does it mean when a resonance has an imaginary component? Essentially, we were able to make a connection between this expression for the modified gyresonance and see that it really comes from a gradient in the electric field. And just from doing single particle trajectories, we found out that when you have an electric field and magnetic field perpendicular to each other, if the electric field has a gradient, it actually modifies the frequency of its gyration. And if the gradient is large enough, it actually causes the electron to no longer gyrate, but actually to be fully accelerated out of the region. And that's what that imaginary component refers to, no longer gyrating, but actually being fully accelerated. And so that's what that physically corresponds to, and it's called trajectory instability in other literature, but it's just essentially a detrapping effect. And so essentially physically what was going on is that due to this profile that we had chosen, essentially this region essentially means that there's electron detrapping happening, that due to the gradient being so large, it's going to just push all these electrons out of this region. And essentially once it does that, it will reduce the density. And essentially we are hypothesizing that this detrapping effect is a mechanism to maintain profiles near this Q equals 1 state, which has been found to be a result in kinetic simulations. And so this is something that we learned about the electron flow in crossfield diodes. So I'll very quickly talk about some PIC simulations. Here we just make comparisons with the theory, and also we just varied the injection of the electron density to see the effect on the growth rate. So just showing here briefly the setup. Now we're showing the crossfield diode on the side. We have the cathode on the left, the anode on the right. We're injecting electrons all along the left boundary. We have the magnetic field here perpendicular, and so we see how we can have the formation of the shear flow instability. I just want to say that as we're varying the injection current, there are a couple important values. There's something called the critical current, which means that when you inject above this current for the electrons, you'll expect the cathode to get space charge limited, which is what we assumed in the theory. And so that's the value that we were keeping track of. And there's also Child-Langmuir law is also another important value when it comes to the injection of electrons. But this is related to just regular diodes. And so here I'm just showing some simulation results when we're injecting above that critical current but below Child-Langmuir law. And so essentially what I'm plotting here is the electron density, where you have the injection from the cathode, and you have the buildup of the electron density, which is reducing the electric field locally. You have a buildup of electrons here at the cathode, and once the electric field reaches 0, you get this expulsion of electron, this layer, and that kicks off what you see here, the shear flow instability that we get from the simulations. Next, we did a comparison between these results and the theory. So here I'm showing the averaged density profile from the simulations in the early times in this early region before we get the instability forming. And we use this input profile into the theory that I talked about before, and from that get a growth rate. And so that's the blue line from the theory, and then from the red line here we have the growth from the simulation, and we get pretty good agreement between the theory and the simulation. And so essentially next we varied the injection current significantly. And essentially, I won't go into the details, but effectively, depending on how much you're injecting the electrons, the initial dynamics of the electrons can change quite a lot because it's connected to what the local electric field is. But ultimately, the end result is pretty similar. And especially if we make a comparison of here, I'm showing from the simulation the growth rates as you change the injection current. If you're above critical current, the overall growth rate is fairly the same. So just wanted to conclude from the theory, we showed a different method that didn't need to have any initial guesses. We learned about this detrapping effect that affects how electron flow works in cross-field diodes. And then we were able to make good comparisons with the PIC simulations and showed that if you inject above a critical current, the growth rate is largely unaffected. And that's all, and I'll take any questions. Thank you.